Good afternoon and welcome once again to the CERIAS Security Seminar. This afternoon I'll be your speaker, Gene Spafford, and the topic of my talk today is going to be the challenge of secure software. Some of the concerns as to why we have difficulty producing software that has security built in and why we have such difficulty securing some of our computer systems. Start off, I'd like to give some thanks to some individuals who've contributed data that I've used in this presentation. Gene Kim, who is the CTO for Tripwire Security Systems, and Dan Farmer, both former students, who are respectively the original authors of Tripwire and COPS. The people at securityfocus.com, website with security information, some of which I have used in a later slide, and three current students working on PhDs in CERIAS, Ben Cooperman, Tom Daniels, and Diego Zamboni, all of whom did some collection of statistical information on some commercial systems. I'd like to start off by saying something about the context in which we work, and that is that computing is present pretty much everywhere today, in nearly everything we do. We find computers not only in the workplace and in government institutions, but we find them in our day-to-day life. Computers are in our automobiles, being used to govern pollution control and fuel economy. Some cars today are being built with local area networks actually present in the car that not only govern engine function and fuel capacity, other issues, but also are hooked up to GPS systems, Cadillac's OnCall, OnStar system that they use for calling out for help, cell phone systems, CD players, and other kinds of electronic devices all networked together on a single bus on our automobiles. We find computers in our homes that are being set up. They're connected to our telecommunications, they're connected to our home heating, telephone systems, even home appliances. It's now possible to buy washing machines and refrigerators that have built-in processors, so you can actually surf the internet while you're looking for something in the refrigerator or waiting for your laundry to get finished. So we're finding computers pretty much everywhere. They're critical to the functioning of many of our social services, our business services, our government services, and our day-to-day life. We really don't need to look any further than some of the stories related to the Y2K preparations to understand all the places that computers have been used and where they are critical to everyday functioning. There was widespread fear that we might have blackouts, lack of food delivery, even the cash supply that we might get out of ATMs might disappear, all as a result of computer malfunctions. Those malfunctions don't have to occur from programming problems associated with a change of date. Those problems can occur because of malfunctions in the software design or purposeful malicious activity. We need to worry about those issues not only because of health and safety, but certainly because of the economy. If we look at the growth of e-commerce in the last decade, we're now up to a $1 trillion a year economy. And small amounts of change there can result in significant loss to us collectively as society and to our individual institutions. What's key there is $1 trillion in e-commerce is a large amount. Individuals who are looking for shortcuts to amassing wealth, instead of writing programs, as many of you will do when you graduate, are perhaps interested in breaking into some of those systems and tapping some of the wealth for their own. So with the net everywhere, with a significant economic presence, and with really a fragile infrastructure, we have a recipe for disaster. If we're going to talk about securing that infrastructure, we need to have some concept of what is secure. What are the basic ideas behind security to define it? And for purposes of this talk, I'll say that basic security involves not disclosing information other than to authorized parties. We don't want to give out financial information, we don't want to give out process information, medical information, or other kinds of information without authorization. We don't want unauthorized access. We don't want individuals accessing those records for any purposes, or accessing our computer systems or our cell phones or any other part of the infrastructure without proper authorization and permission. And we don't want them to make changes, whether those changes are to the records, the data, the programs, or the entire operating systems that govern the use of those systems. So we want to regulate the access and the ability to make changes. Quality of service is important in these systems. We want the systems to continue to operate and process in a timely fashion. It does not help us to get medical information days after it's needed in an emergency room. And it doesn't help us to do stock trades hours after changes in the stock price. Many of our applications are critically dependent upon our ability to retrieve information, process it, and display it in a very timely fashion. And to do that under load. That's something that we need to preserve. Issues of audit, authenticity, and control are important. We need to be able to monitor our systems to know who has used them and how they've used them, so that we can go back afterwards to correct failures, do correct billing, and possibly to correct mistakes, or even to go after people who've misused the systems. All of those are an aspect of security. In short, we want systems where there are no surprises, where the systems work as we require them to work, where we know what happens, we can control who makes those things happen, and that after the fact we can tell how they happened and when. But the critical concept on this is we have to start having security out of the box. When we put systems into place and start using them, the security needs to be present from the beginning. It cannot be an add-on, something that we have to put in later, because too often it will not be added. It will not be present, or the systems will be misused or misconfigured from the beginning because the security isn't there. Without that assurance that our systems are secure from the moment they start being used, we're going to endanger our economies, our safety, our privacy, and our institutions, because we will have systems in place that cannot be depended upon, that provide us surprises, and surprises of the wrong kind. So how are we going to get there? How are we going to have those systems that have no surprises and that have security in place? How are we going to have them so that they are secure from the beginning? Well, I believe that there are some basic principles that we have to bear in mind if we are going to design and deploy security in the broad scope of society. The first one is understanding the needs of the users. We need to understand who our users really are. Part of the problem is that those of us who are involved in the design and the programming and the development of computer systems work day to day with educated, concerned individuals. We work with people who are comfortable with technology, who have access to the technology, and who understand complex concepts. But worldwide, the majority of users of computers don't have that level of sophistication. Many of the users already online or coming online have limited ability to read, to write, to understand the technology. They are typical average people. And those of us who design systems don't really have as much interaction with typical average people. The ones who are using computers now, who are looking to be on the net, they are exchanging email, they're in chat rooms, they're buying things off the network, are the same people that we encounter perhaps bagging groceries at the grocery store, or holding up the flag at the construction site on the roadside to keep us from driving through. They are people without the level of education and perhaps sophistication that we have when we build these systems, although not true of everyone. And as a result, some of the things we build in and some of the assumptions we make simply don't hold. When we assume that they'll understand that they need to put in security settings, or they need to deploy virus protection, or they need to worry about firewall settings, we're making assumptions that really don't hold. Those individuals don't understand. As a result, those settings don't get set. Those protections don't get put in place. That software does not get installed correctly. And that leaves their systems vulnerable. We have failed in our job as professionals to protect the user population. And at the rate that the computer usage is growing on a worldwide basis, more and more of those individuals are going to be coming online in the near future. A second aspect is we need better understanding of security. There are some basic principles behind secure design, but we don't often teach those in standard computing courses or curricula, and very few companies have experts who have training in security who are involved in designing systems, deploying systems, or testing systems. Third aspect that's important is a software engineering one. If we're going to have secure systems, then we need to capture requirements for security early on before we begin detailed design. Those requirements need to be expressed and then translated into formal specifications. We need to actually build into the design appropriate mechanisms for us to have security in place. Security should not be an add-on because it will miss things. It needs to be built in so that it is transparent and available. But that means building it into the design early on. We don't do that. In fact, most software does not seem to be designed at all, but rather just thrown together. In part, that's because of tools, because of training, and because of internet speed, where we need to produce software and systems and get them to market so quickly that some of the standard steps of careful design and testing don't seem to occur. We need to design with those good tools and methods, and they take time, and they take expense, and they take training. And then afterwards, we need to validate and verify the systems that we've produced to ensure that they meet the requirements and the specifications that we've established for the software. I mentioned about understanding users, and part of that is understanding the range of users. Not only the average user, but the range. We have a range from experts to fools. And unfortunately, as with many other areas and technologies, a great many of the fools believe they're the experts. There's a wonderful line that I found a few years ago on the net that said the problem with the global village is the global village idiots. And that's certainly true with a lot of our network systems and e-commerce. When we put things out there, we assume that people are going to use them the right way. But it's the right way as we designed it, without thinking about all the ways it can be misused or misunderstood. Another thing that we're failing to keep in mind for that user population is that the requirements and policies differ greatly from one environment to another. What seems to be a reasonable policy to us in a university environment would never work in a bank or a government agency because their requirements are very different. As I have often said in some of my classes, if you think about the standard policy for a military agency, there it's perfectly acceptable if you blow up the computer system, shoot all the users, and set fire to the building, so long as you don't read the information. That's a military policy. Securing the information is more important than preserving the processing or even the user base. That wouldn't work very well in a bank. Some universities perhaps, but not in general. As a result, we design systems for a particular policy environment, and we don't do a good job of creating the mechanism and the alternatives to allow expression of other policies, other protections, and supporting other requirements. That's failure to understand the user population. The fact that we have high security systems, real-time control, national weapons labs governing security of our most sensitive weapons, all running on the same operating system that you can buy at Walmart for $89.95, should be a concern. At least it is to me. And yet, that's the mode we're in. We're letting price drive our ability to determine different requirements, different policies, and supporting mechanisms for those different policies. But that's what vendors do. We can't really fault them from trying to generalize their designs to maximize the market, maximize the profit potential. And when they are selling to such a wide population, they generally ship that software with the lowest possible settings so that the users who are least able to understand can just turn on the system and not have things get in their way. From a vendor standpoint, the biggest cost is in tech support. If they can minimize the number of calls to tech support, the number of returns, and the number of problems people report, then they save money. Therefore, they put the least obstacles in play. And that fails to take into account the need for a broader variety of policies. For us to understand security means we need to limit what happens. We need to limit who makes it happen, how it happens, and limit who can change the systems. That, in large part, is something resisted by users. Users don't like limits. They don't like barriers. Users have systems and they want to use them to the full potential. Users don't tend to like safety guards on things. Not simply computers, but any other kind of appliance. Users don't like speed limits. But we have to provide those if we're going to have good security. Unfortunately, our history with computing has been to supply systems without those limits, because we have spent a great deal of time and effort trying to make systems work. And when you're trying to make system works, you need to have access to the insides. You need to have access to the special functions for debugging and monitoring and tweaking to make sure that things do work. So now, to supply systems that don't have those capabilities, that do have guards in place, seems alien to many users. That's a problem. About the only way we're going to change that is to create a paradigm shift in the way people look at computing. For a very long time, as an example, for a very long time, the population in the US resisted metered phone service. Because early on, phone service could only be supplied through mechanical switches, and it was very expensive to meter how much of the phone service you used. So initially, for cost and for reliability features, the phone companies would provide phone service in a local calling area on a flat rate. And every time the phone company tried to establish a metered rate, users would complain, they'd go to the Public Service Commission, there'd be hearings, and no one would select that as an option, even if it saved them money. But as a paradigm shift, if we look around at all the people with cell phones now, we're all paying metered rates. 10 cents a minute, maybe with a bulk charge up front, but we're used to that concept now. We use that for metered service, local area service. What we have to do if we're going to put security out into the population is perhaps have a paradigm shift, like switching to Palm computers, or switching to wireless or thin clients, or maybe the wireless paradigm is a way to go. But to get through to users, to overcome those preconceptions, that history may very well require that we do some kind of significant shift of the way people compute. I'd like to present here some old, classic security design principles. These were developed back in 1975 based on some very deep thought and long study of a number of computer systems and security problems associated with them. It was a paper that was published in a national conference in 1975. But if we look back at these principles, they are still very, very relevant to computing of today. And many, if not most, of the security failures that we are seeing today are related to failures to adhere to these principles. Why we don't pay more attention to these is a mystery to me. Hopefully we can learn something from these and begin to apply them. I'll talk about each in a little more depth. The first is the concept of least privilege. And least privilege can be traced to perhaps the oldest security principle known long before computers. It's need to know. It's need to access. If we limit privilege to only those processes or individuals or capabilities necessary to do a particular job, if we don't give away too much authority or too much access, then we may be able to limit the damage or the disclosure if someone wants to misuse that authority, or if something goes wrong with the system, or if somebody else is able to figure out how to gain access. Give the least access necessary. We see this not only with computers, we see this with classical information flow with papers, and even with issuing of keys. We don't give everybody a master key to a building. We limit the number of people who get access to those keys and to submasters, and give only the keys necessary for people to access their rooms or do their jobs. On a computing system, to limit access or at least privilege, we want to create protection domains. Domains of information and activity that are limited to particular tasks and grant access to only those domains necessary to carry out a function. No superuser is involved in a system that has least privilege, because a superuser is the equivalent of a master key. A superuser has access to everything, and that's not necessary to do most tasks. Fine-grained access control lists, real capabilities, or something similar are the way to go in design of a system that has least privilege. But those tend to slow down a machine. Role-based authentication is another area that's being explored in research that can be used for least privilege. Enforcing confinement properties is part of least privilege. But these don't match the desktop-based model. These don't match what our users and ourselves are used to having access. When we look at our desktop, we have a computer where we control everything. We have super user access on that desktop, or we have, in the case of a PC type machine, we have the ability to install any software, reboot it in in administrator mode. We can go out on the disk, change any sector. We have full and absolute control over that desktop system. That's not least privilege. And that model will not succeed if we wish to have a higher level of security. Second general principle is economy of mechanism. And that is, any code that performs privileged or restricted operations should be small, simple, and easy to verify. That the security should be built into it rather than added on, so it is intrinsic to the unit. Small unit, easy to verify, using proven methods. Well, this doesn't match well with feature-rich design. Talking about small and easy to verify doesn't match well with operating systems that have millions of lines of code, or in the case of one popular operating system, tens of millions of lines of code. How is that small and easy to verify, particularly as a monolithic operating system? When we have word processors that have 10 million lines of code that go into them and give you options to lay out text in multiple colors, blinking in circles, in 15 different fonts. How is that small, focused design? It's adding features that the majority of users never need, never want. Spreadsheet programs that allow you to automatically send email from the spreadsheet upon receipt or opening a spreadsheet document to everybody in your network address book and enclose macros that you don't even know are there, is not small and feature-rich design, particularly when that same spreadsheets program has a flight simulator built into it. Understanding economy of mechanism, keeping things small and simple and easy to verify and understand, is a critical component not only of good security, but of good software engineering. Quality software engineering, to keep out mistakes and bugs and misunderstandings. But that conflicts with what users want. Users want more features. Putting out new revisions that have lots more features tend to attract people to go out and buy upgrades. People to go out, buy new versions, buy memory to support the new versions, stand in line at midnight to be among the first to buy the new versions. That's a mindset problem. It may require a paradigm shift to change, but it directly contradicts good security design. Complete mediation is a principle here. Every access to critical resources should be checked. For instance, with a security kernel, or real capability, such that every access requires an address pointer with a capability. But this conflicts with speed and performance. Real capability-based machines, real security kernel machines, are slower because they require that mediation, that require extra cache misses, extra lookup for address translation, extra software steps. And it doesn't map well to things like the World Wide Web or our typical usage, where we want to log in once with a password and thereafter everything occurs without any further check. Or on a web access where we make one reference and type in a password and get a cookie and everything thereafter is downloaded from all other sites without any further checks. Or with email, where once we've logged in and we start receiving email, all email that's addressed to us, all macros, all attached documents come in without further check. All of those things are conflicting with the idea of complete mediation, where we know what we're accessing, that accessing is checked, and we have explicit authorization for each action and access. There's the issue of open design. Open design has often been misinterpreted since that early paper. Open design was primarily discussed in the context of the paper as for cryptographic algorithms. And the idea behind open design is that the security should not depend on the design being kept secret. But keeping the design secret can add security. Your system should be secure even if the source code is published, whether it's a cryptographic algorithm or a security kernel. But if you keep that information secret, that can add additional security above and beyond the algorithms. And that's a principle that was well known and understood back in the 70s, and still to this day. Open source is a different argument. Publishing the source does not lead to greater confidence in the source per se, although compared to many commercial products today, that could be the case. In general, publishing source or not has not proven to be the sole factor in having better code. In fact, some of the most secure systems that were ever produced that achieved B3 or A1 ratings under the common criteria precursors, under the Orange Book, the trusted computer evaluation models, were all proprietary systems where the source code was not only proprietary but classified. But those systems were very carefully produced at great expense with software engineering tools, closely examined, formal proofs of some of the software and containment properties were provided, and they were very, very secure. The fact that they were kept secret and classified added to the security that was already present. But that secrecy didn't provide the only security. It was simply an addition. Separation of privilege is an important principle in security. And that is that access should require more than one authorization if it's logically sensible to separate. That is, we shouldn't have one access being a password, one login, one set of commands issued, one key turned in a lock, one smart card inserted in a reader, and everything thereafter be allowed. Instead, that should give only the authorizations necessary associated with that access, and everything thereafter that requires additional authorization go through some further step. Another example here is the separation of privilege involved in macroviruses in email. The privilege, the ability to download email and read it, is and should be something separate from the ability to run a new program and send email. They shouldn't be grouped together because they are logically different functions. Email that can be read shouldn't automatically confer the privilege to send out more email, especially to a large global address book. If that separation isn't in place, you have problems such as what we've seen with Melissa, the I Love You virus, and other problems. Another model here that is a common problem in most current operational environments is having the system administrator also being the security administrator. If the person who installs and maintains all of the security programs is also the person who audits the logs, responds to the alarms, and decides what's a problem, you don't have that separation of privilege. You don't have a necessary separation to keep that person from causing mischief and then covering up the alarms afterwards. Again, this doesn't map to the desktop computer. Least common mechanism. The idea here is to try to generalize but not too far. It's a good idea to reuse code, especially if you've put a lot of time and effort into getting that code correct. But continuing to generalize the code, continuing to try to do too much from the same software leads to problems. Because you have to keep adding more conditional statements, more special cases, more code, you get further and further away from that nice, compact, trusted bit of code that you had in the first place. As a result, you have additional information flow through the system that can be snooped or diverted or copied. And you have the additional possibility of race conditions and logic errors. Unfortunately, the idea of least common mechanism plays havoc with the idea of backwards compatibility and reuse. If we want to go from one system to another, we want to move forward and add new features, we want to reuse the old code and add on to it. But if we reuse the old code and add on to it, we're not using least common mechanism. We're making it more complicated. We're creating new paths, new possibilities, new functions that may be abused. And last, and very important, something that we often overlook as technologists, is psychological acceptability. And this gets back to understanding the users. Code that's going to work well, code that's going to be accepted and used, should be code that's as easy to use as it is not to use. That is, if we have to go through a great deal of effort to use some new feature, users will stop using it or find a way around it. And that will lead to problems. If it is harder to log in with some kind of security device, like a one-time password generator or a proximity card, if it is significantly harder, users will resist it. They'll go back to something simpler, unless you have very significant penalties in place or a very well-educated user population. So it's very important that the psychological acceptability of whatever measures we put in place be such that users can use it, maybe even want to use it, that we couple it with benefits, that by using some new mechanism they actually are better off than not using it. Second aspect of psychological acceptability is to reduce false alarms. When we build in security systems such as intrusion detection or antivirus systems, and they generate false alarms, once or twice, occasionally, that may be all right for the typical user. But if you get a false alarm on a regular basis, users will shut the system off. Or they'll start ignoring the alarms. And once they start ignoring the alarms, they'll stop paying attention to events that have real alarms, because they're ignoring all of them. That's a psychological acceptability issue that needs to be dealt with in the design of most security systems. Frequent changes and updates are bad because they have a low psychological acceptability. People want to use their systems, not spend all their time updating them. If you have a computer system and every week you have a new security alert, a new patch, a new upgrade that needs to be applied, eventually you will stop applying those patches or upgrades in a timely fashion, and you may stop applying them at all. Even worse, if you're a typical system administrator or security administrator, you may have hundreds or even thousands of machines to administer. And every time you have to put in a patch requires that you schedule it, you worry about critical downtime, and you have to worry about deploying it on all of the systems involved. The more systems involved, the more patches involved, the less likely you are to apply that patch in a timely fashion if you apply it at all. And that's a major problem. Another problem is that patches shouldn't require great expertise to get correct, or the measures we employ shouldn't require great expertise to get correct. If you're shipping out new security fixes, new patches, new programs, and it requires somebody with certification or a degree to apply them correctly and keep the machines from crashing, again, not everyone will apply them, or they won't apply them as regularly as they should, and that will lead to difficulties. That will lead to poor security. There's also a combinatorial problem. I don't have that listed as a bullet on the slide, but if you have too many patches and they don't work well together, or they require a particular order, you run into problems with administrators who may leave one out, may not hear of one, or may apply them in the wrong order and then disable the machine. Again, that's very poor from the standpoint of getting users on your side, willing to apply patches, interested in applying patches, and willing to have security measures in place. It simply doesn't match the user population. I would say that the big problem with patches is that they shouldn't be there at all. You should be designing good security in from the beginning. That the penetrate and patch approach really doesn't work very well. But that's because we have poor software engineering. We don't apply the technology that we know. We don't apply what researchers have found. We don't apply the tools and techniques that we already have at our disposal. And as software gets bigger, the problems get bigger. They get more frequent. We know from software engineering that problems occur most often at the interfaces. So as we have larger and larger code bases, more modules that are programmed by different individuals and put together, there are more interfaces, there are more points at which errors can occur, and it's no surprise that we get more problems. It also shouldn't be a surprise to us that as we continue to use what are known to be dangerous languages, or I should say languages with dangerous features, that as we get more problems and more security flaws, well, as I said, that shouldn't be a surprise. So why are C and C++ dangerous? Because of unconstrained buffers. It's easy to overflow buffers. Pointers and pointer arithmetic. It's very easy to go out and alter things in memory where they shouldn't be altered. Types can be overflowed or written over each other. Some of the typecasting that goes on can result in truncation or bad conversion without warning. We've known this for a long time. These kinds of problems, these software engineering problems, have been known by language designers, software engineers, and OS designers. So why do we use those languages? Well, in part, they're good for some things, like writing operating systems or device drivers, where we need to be able to access in certain locations in memory, or we need to coerce data types. But because some systems, some software have been written in those languages, and people know the power and expressive nature of them, they want to continue to use them. They want to continue to use the legacy code instead of using something safer. So these old mistakes continue to be made. We reuse old code that has those mistakes in place. We reuse routines from libraries that fully support buffer overflows, for instance, or bad pointer arithmetic. We continue to write code without any formal requirements capture. We continue to write code without any formal specifications development. We have code that's written to ad hoc specifications and requirements. And as long as that's true, really from a formal standpoint, if you have code and there's no formal specifications, there's no formal requirements, then the code can never be incorrect. It can only be surprising. If you don't know what it's supposed to do in a formal way, you can't say whether or not the code is doing it. And you can't test to see whether or not the code is doing that. We also have a problem with poor internal documentation. Too many coders don't like to write comments. They don't like to document what they've done. And as a result, people who go back in to maintain it don't understand what the code does and tend to compound the errors. All of these are known problems. All of these are things that we've been facing for years, and certainly as faculty we try to teach students not to indulge in this behavior, to use better tools, use better techniques, but that doesn't succeed in internet time and standard software development out on the internet. Testing. Testing is important, but it's an economic consideration. Testing requires expenditure of funds. You have to invest in tools, you have to invest in trained personnel, and you have to invest in time. Time translates into an opportunity cost. If it delays your product to market, someone else may be there with a competing product before you are. Or your customers or your stockholders may lose confidence because you're taking too much time to get something ready. Therefore, as an economic consideration, you are disinclined to test. And if testing requires that you spend time making out full requirements and specifications so you know what it is you are to test, again, it's going to cost money. So many firms don't bother to test unless there is a strong economic incentive otherwise. Unfortunately, we don't provide that economic incentive in most environments. Only in some very safety-critical environments are we likely to do that. And for that, we should be glad. Certainly, the next time we're on a Boeing 777 or Airbus 320 or 330 and they're coming in for a landing, we really don't want the pilot to have come up on the glass cockpit, abort, retry, fail. That would be very unpleasant. Some of the statistics that have been gathered from major vendors indicate that when they release software with known flaws, users only complain about 5% of them. So why should they spend effort trying to find 100% when only 5% ever seem to be noticed or cause problems? Users provide workarounds for the other 95% or never encounter them. Of course, that may be because most of the software is produced as so many features users never use. Now, it would be a lot simpler if only we knew what 5% would be found, because then we could just fix the 5% and leave the other 95%. But we don't know how to do that. I want to give some rough numbers for magnitude of the problem to give you an idea, just in general, of some of the problem. I'm going to start off with some very conservative assumptions. First assumption is there's no perfect code. Nobody writes perfect code. There may be people capable of writing perfect code, but we're far too busy. We're going to assume a conservative rate for introduction of errors and flaws into software. Assume that in unaudited code, that is code that's not read over by others, it's not carefully examined for flaws, there's one security relevant flaw per 1,000 lines of code. That is, for every 20 pages worth of code that's written, there's one error. I would imagine that if you think of your own experience in writing code, you'll realize that's a reasonably conservative estimate. And we'll give a certain benefit of the doubt to code vendors, producers who audit their code, who do a more careful job of looking through the code for problems. And we'll say that there's maybe only one security relevant flaw for every 5K lines of code, about 100 pages. And then I've listed 4 operating systems and their approximate number of lines of code that are present in those operating systems, and use the numbers on the left to derive a general number for the number of security relevant flaws that may be present. Those are not a small number of flaws. And those are the systems that we are using to build our e-commerce systems, our medical systems, government systems, even our defense systems. There's a problem there. And this bears out the problem, at least as the order of magnitude goes. This is taken from the folks at securityfocus.com. They broke out the number of reported security problems, not general flaws, but just security problems for each of the different operating systems. And if you were to map this back on the previous numbers, you'd see that the orders of magnitude are just about right. The systems that have had the most security flaws reported are Linux and Windows, followed by CERIAS and AIX systems. All of this is really an issue of quality. And quality is really driven by the marketplace. All of our products that we have a feedback mechanism built in for quality. Products that are produced that have poor quality tend to generate poor reviews, poor repeat business. In every market except for software. It's amazing. We can think of many instances of software really poor quality. Software that crashes, that misbehaves, fails to perform according to specifications, and yet what we do is go back and buy more. We buy the next edition of the software, hoping somehow that all of those problems and that quality, that lack of quality, will all magically disappear in the next release. It's amazing that we have been trained and we've developed this kind of faith in that technology to believe that suddenly all of the programmers will suddenly get it and will suddenly be able to produce code without problems. And it doesn't happen that way. It doesn't happen that way because they don't have time to learn. Good quality software engineers are hard to find. Programs that teach it well are rare. And within the organizations, you'll find that a small number of programmers are very good, the others are not so good. What really should be done by the companies is that they should invest money to make those coders who aren't as good, to make them better. But companies don't do that. They don't invest money in trying to make their programmers better because then they lose them. The market is so hot and there are so few people who are really, really good coders that if a company raises the level of its personnel, it will cost more to keep them, and it would be, and it very often happens that they leave for another company with better offers now that they have better skills. So we see some life cycle issues. Most commercial products right now, it's from the big companies, they identify a need, they justify it internally, they implement it, and then they sell it, sell it, sell it. So you see brand names, you see major brands that are changed only a little over time. And usually those changes are to add more features and to fix bugs and introduce new ones. Although that last part is not one of the things that the marketing department likes to advertise. Although oddly enough, when Windows 98 was released, there was a fascinating ad that was in a lot of the journals from Microsoft that said, you'll want to upgrade from Windows 95 to Windows 98 because it fixes the thousands of bugs present in Windows 95. Gave me a warm, fuzzy feeling. Of course, I have a fuzzy feeling most of the time, but one has to wonder at what would prompt them to use that in advertising, to admit that the previous product had thousands of bugs, and they wanted you to upgrade to a new, larger, more complex version. But again, the market is such, people buy that. People go, yeah, that's a good reason to buy the new version, and go out and do it. I'm sure many of you did as well. Of course, then there are the open source projects, and Guy Kawasaki, this was a great characterization. With open source, you fire, then you aim, then you fire again, then you aim again, and repeat. Basically, you have a lot of code geeks who go, hey, this would be nifty. They program it and then see, does anybody want it? And then they go off and program something else and see if anybody wants it. Which is why you find all of these really strange additions into things like Linux. Device drivers for devices that nobody could possibly want, but they're bundled in with the rest of the code and there to introduce their own set of bugs and problems. And then there's the disruptive product lifecycle, which is used with a lot of small startups. You get an idea, you get just enough funding, and you spend just enough time to ship something. You get it out on the market, you have just a little bit of budget to respond to complaints and put patches in place, and if it turns out to be successful, if it really sells well, then you go IPO and everybody retires or goes off to start another company, so there's no expertise left to maintain what you just shipped. So let me restate these problems that I've been talking about in a very general way. We have a problem with internet time in the current market. There is incredible demand for new software and for the people who produce it. User expectations have been cultured to be low. There's a lack of consequence and liability for poor software, poor quality, and poor design. Otherwise, we wouldn't be ending up with code that had all these embedded Easter eggs, things that appear in the code that we didn't ask for, we didn't want, and aren't documented, but make the code bloat up to megabytes worth of size, requiring us to buy extra processor and memory simply to accommodate them. We would not have things like the concept macrovirus. And I use this as an example because it typifies a vendor attitude. Back in 1996, I believe it was, the concept macrovirus appeared. It was the first macrovirus for email. It was not the first macrovirus, because those of us who were doing research in malicious software back in 1990 were talking about macroviruses at security conferences. They were well published in journals and in conference proceedings, but the major vendors didn't pay attention. So in 1996, the folks at Microsoft shipped a developer CD worldwide that had some example macros and software and other things for developers to get a pre-release look at new capabilities. And embedded on that CD-ROM was the concept virus. It was a macro that, when run, would generate other macroviruses using Word version 6. And as a result of being on that developer CD and shipped worldwide, it sprouted up in hundreds of places within a matter of weeks. Worldwide spread very, very quickly. The response to this was fascinating. The people at Microsoft did not respond by disabling the features that allowed the virus to spread. They did not issue a patch that would prevent these kind of viruses or detect them. In fact, they didn't even attempt to track down the person who programmed it and put it on the CD-ROM. Instead, they issued a release calling it a prank, something that users could ignore. Which is why currently we have somewhere in the neighborhood of 7,500 to 8,000 macroviruses, with about a dozen new ones being reported every week. And they have had no liability, no action taken as a result of this. Changing the environment, introducing this kind of liability, dismissing it as a prank rather than as a security problem, and not taking immediate action to provide any kind of defense against it. And we all accepted it. Another example from the same company, and the reason these examples are there is because they have so much of the market share. About a year and a half ago, it was disclosed that there was a hidden passphrase inside Internet Explorer. That if you typed Netscape engineers or weenies backwards, the reverse of that, then it would give you some additional privileges in accessing Internet Explorer and accessing what was on disk. Well, this made the press, and the head of Microsoft Security was quoted as saying, "If we can determine who did it, we will take action." Now that, to me, is a disturbing thought, that a major software platform that is being used worldwide for all kinds of application, from real-time medical control to internet banking, is being produced and shipped with no version control to know who put what in the code and how it got out there. No way of knowing who wrote the code to take action against them, no way of knowing when it was introduced or what's in the code. That's a disturbing thought. And again, it just went right by and nobody commented on it. But that's because it's not unusual. That's the way code is produced. And as a population, we're allowing that. We don't take action about that. So what can we do? Well, we can start by increasing awareness. Understand that there isn't any average user. Understand that there are balances between features and security. Adding new features and functionality is not necessarily a good thing. We need to employ better testing. In fact, some companies could employ testing, period, and they would be doing better. We can do a better job of managing complexity and change, using some of the tools and techniques that we already know about. Build in security from the start. Make that one of the design goals. And as consumers, make sure that that's one of the features that we demand in what we purchase. Understand policy differences. Understand that not everybody wants the same set of restrictions, and that not everyone can tolerate the same set of restrictions. Basically, we need to be better consumers as well as producers. Why do we want an operating system that has 30 million lines of code? Why does that give us something that other systems don't? Especially when 90% of our users are only going to use the platform for email and word processing, possibly some others for spreadsheet. Even though there may be tens of thousands of different software applications, the majority of users never use them. In fact, studies have shown that most home users run on average 1.5 programs on their PCs when they buy them. So why all the other functions? Why all the other capabilities? As consumers, we need to start demanding quality and security better instead of new features. We need to understand that those systems are important, and we can't tolerate spending minutes or hours a day staring at blue screens, staring at reports of viruses, trying to clean things out of our mailboxes, or otherwise having to deal with all of the various quality and security flaws that may be present. The security and quality aspects need to be measured. When we buy software, we buy systems, we need something that tells us what's been done to the code, rather than simply getting numbers to say that it is faster or that it runs more programs. We need to have measures of quality. What kind of coverage testing was there? What kind of path testing? Was it produced using one of the ISO 9000? Was the production team certified ISO 9000? Those are the kinds of things that we need to know and we need to begin asking for. And we need to understand that the penetrate and patch approach isn't security. Hacking into systems isn't security. Pretty much anybody can hack into a system. Designing it right in the first place is much harder, takes a different skill set, and an important skill set. Simply breaking things is not a way of testing them. Crashing cars into walls isn't a good way to design safe cars. It may be a component, but you have to do far more in advance to get it right before you get to that stage. We're not doing that in software. We need to find ways to motivate vendors to embrace quality and embrace security. It can be a sales differentiator. How do we convince them of that is the question. Well, I think one way is that lawyers are about to get involved in this arena. And oddly, in this case, lawyers may be our friends. It's not often the case, but maybe here. Because when you have a company that loses hundreds of thousands or millions of dollars because of a software failure that could have been anticipated, or that was based on software quality issues that were known for decades to be a problem, the lawyers are going to come in to try to recover the losses. The officers of the company have a fiduciary responsibility. They have a responsibility to the shareholders to try to recover the losses, because they don't want to be stuck with the bill. They want to shift the losses onto someone else. And the vendors are the ones with the deep pockets. They're the ones who've been making the money. And they're the ones who could have very possibly prevented the problem. So the lawyers are certainly going to get involved here. That may help push some of the vendors to apply some well-known methods. But interestingly, the vendors have already anticipated this. And instead of employing better security and better quality assurance, they've instead been funding their own lawyers. And they've been on an offensive of their own. The one I'll mention here is UCETA, where the companies are trying to hide behind the law in an attempt to protect themselves. You can visit the site www.badsoftware.com, bad software is all one word. And you'll find some information on UCETA. In brief, many, many years ago, in an attempt to harmonize contract law and sales law throughout the United States, a group of attorneys and salespeople and industry representatives and state government people got together and came up with the Uniform Commercial Code, the UCC. This was a set of laws designed to govern commerce that were then sent to all of the 50 states around the country, and the individual state legislatures adopted those, some with minor modifications, to govern contracts and warranties. So if you buy a product in Maryland or Florida or Michigan or California or Texas, your rights under the law are pretty much the same everywhere. It's not a federal issue, it's a state issue in each state. Well, as e-commerce has grown and as the network has grown, and as more and more has occurred in this arena for electronic commerce, gaps have been found in the law. There are ambiguities, there are problems, especially if we're going to sell things over the network. So a new conference of lawyers and vendors and representatives was convened several years ago, and they began work on an update of the UCC. And some of the companies paid a lot of money to send in a lot of lawyers and a lot of representatives that dominated the process, to the point where many of the lawyers and the representatives withdrew. They said they wouldn't be part of the drafting anymore, which of course was just fine with the group that was dominating the debate. And so they ended up producing UCETA, which is about a 200-page document of dense legalese, very hard to read, that's been submitted to all 50 states for passage. And if you read it carefully and you understand the technology, you'll find that it gives vendors the rights to enforce a contract on you that you haven't read at the time you buy the product, because it's inside the package. It's no longer on the outside. And the vendor can update that license at any time they want by sending you email or by posting a new version on their website. And they can build in a feature to the software that allows them to disable it remotely across the network, and that you have to leave a hole in your firewall to enable them to do that. And that you're not allowed to publish reviews that are critical of the software without their written permission. And you're not allowed to reverse engineer the software without their permission, even if there's a virus present, or even if you suspect that it's divulging confidential information. And if you use their software and it fails and causes any kind of damage or loss, you can't sue them. Isn't that a nice set of provisions? And there's more, but that'll give you an idea. So you'd think to yourself, who in their right mind would ever pass this? Well, let's say the state legislature in Maryland and Virginia, for two, they've already passed it. It goes into law. The governor signed it, and contracts and purchases in those states are already are ready to be governed by the law. Interestingly, Iowa state legislature has passed a law specifically prohibiting UCETA provisions. So the folks in Iowa at least have a clue. But the other states are considering it, including Indiana. Why would this get passed? Why would it be passed when ACM, IEEE, the American Law Association, the American Bar Association, the Recording Industry Association of America, and the Consumers Union, state attorney generals from 26 states, and about 50 other organizations are all on record as opposing it? Well, because three major entities are supporting it: Sony, Disney, and Microsoft. They're putting a lot of money behind the lobbying, and they're claiming that they won't want to do business in states that don't pass it. So of course the people in those states are passing it or considering it. That's my view on it. I would suggest all of you as computer professionals visit the website, read the materials, follow the links, formulate your own opinions. So in conclusion, I want to say better security is possible. The things I've just outlined to you really don't require very complex mechanisms. We know a lot of the technology. We have the tools. It's simply a matter of wanting to apply them and making them economical to apply. Our best hope in the near term is to get some major vendors to want to use quality as a marketing feature, that they should make it a priority to protect themselves, to protect us. but I would say don't hold your breath. It's going to take some crises to make a difference. We haven't seen them. Y2K offered some possibilities, but we did too good a job cleaning up from it. So it may take something else of major proportion before people really get worried and really get angry. And with that, I'll take any questions that people may have. Well, that's great. I've either put you all to sleep or it was too clear. Thank you very much, and we'll see you here next Wednesday at the same time.